Today, I'd like to think about particle motion in this Schwarschild field that we've recently been talking about. Subtitle, Thinking of You. I'm going to think of having some pathway that a particle may be following, described by some parameter lambda or the other. I'm going to define the vector u as the derivative of the position with respect to the parameter. In special relativity, or in a locally Minkowski coordinate system, I could use proper time of the particle for the parameter lambda. U is simply the 4 velocity, and u dot u will be -1. On the other hand, if I'm talking about a photon or a pulse of light, then u dot u will be 0. We don't call that the 4 velocity, even though it is a tangent vector. There are two additional pieces of information we need to remember before we can proceed. Firstly, if we look at the situation where the tangent vector never changes, the same argument that we've used before leads us to the same set of equations that tell me the geodesics. The second fact is, if there is a certain specific index alpha, so that no metric tensor component depends on x number alpha, then if you travel along a geodesic, the lower alpha component of u is constant. We raise and lower indexes on tensors and vectors in the usual way. Recalling what the Schwarzschild metric is, you'll notice that no component depends on the time coordinate. Therefore, u subscript 0 is a constant along a geodesic. Also, no metric tensor component depends on theta, which is x number 2, so u subscript 2 is a constant along a geodesic. Since u subscript 0 is a constant, I'll make up a name for that number. I'll call it -e. We know how to raise and lower vector components. The metric is diagonal, so that out of all of the g0 alpha numbers, only g00 is different from 0. Divide the -1 minus 2 gm over r out, and we find out that along a geodesic, component number 0 of the tangent vector is given by e over 1 minus 2 gm over r. Of course, that's the same quantity as the derivative of coordinate time with respect to proper time. An interpretation of this could be thought of this way. If r is very large, so that the gravitational potential is small, then dt d tau is approximately equal to a constant, e. If the particle is moving slowly, so that its kinetic energy is also small, dt d tau should approximately be 1, so the e should approximately be 1. The constant e tells us how the position in the field and the motion of the particle cause the relationship between coordinate time and proper time. The statement that u subscript 2 is a constant eventually reduces down into d theta d tau is constant over r squared sine squared phi. Before I go on, I want to make a little side comment here. The Schwarzschild field is spherically symmetric. It's not unreasonable to think that we might have some particle trajectories that lie within what we would ordinarily call the xy plane. That is to say, phi taking on constant value pi over 2. If that were to happen, I can rewrite that last equation in a more revealing form. Now we find out that u sub 2 being constant within this air quote mark plane, phi equal pi over 2 represents conservation of angular momentum. The h is the angular momentum per unit mass, and it is constant. Continuing to think about a material particle, u dot u, by definition, is g alpha beta u alpha u beta, but on the other hand, u dot u is frame invariant. At a given point along the path we're interested in, we could evaluate u dot u using a locally Minkowski system in which we know that u dot u is -1. If we were talking about photons, u dot u would be 0. But again, dot products are coordinate system invariant, so instead of using a locally Minkowski coordinate system, I could use the Schwarschild coordinate system. We know that the metric tensor in those coordinates is diagonal, so there are only going to be 4 terms to look at. In 2 of these 4 terms, though, I have a component of the tangent vector, which for material particles here we can also think of as the 4 velocity, that I have mathematical expressions for. If you will review the video about what would Isaac Newton do, this is beginning to resemble that very much. So let's do the same kind of algebra and calculus that we've done before, and also I'm going to build in the assumption that phi is constant at pi over 2. Since phi is a constant, d phi d tau will be 0, and I can disregard this last term. I'm going to multiply through by 1 minus 2gm over r to simplify things, and then we have 2 substitutions to do. One of them was r equal 1 over u. The other was to change the variable of a differentiation from whatever the parameter was, tau in this case, to the angle theta, making use of conservation of angular momentum. So just multiplying stuff out, we get this second equation. What I'm going to do now is I'm going to convert the r's into u's, and also I'm going to do derivatives with respect to theta instead of with respect to the parameter. After doing the appropriate chain rule and algebra, we're led to this equation. Once again, using what would Isaac Newton do as a model, I'm going to differentiate this with respect to theta and see if I can't extract an equation from it that will describe the motion that I'm interested in. Next, divide through by 2, divide the du d theta out, and divide h squared out. Finally, we obtain this differential equation. It's worth mentioning that we've been doing all of these calculations in units where the speed of light is equal to 1. Since radians are dimensionless and u is 1 over r, the units on both of the terms on this side of the equations are reciprocal length units, 1 over meters. In meter kilogram second units, if you work out the details, you also get reciprocal units of length for this term, but you don't for this one. In that last term, if you want the units on the term to come up reciprocal meters, it turns out that you're missing 2 factors that have the units of a speed. When the dust finally settles, the differential equation that this u function must obey is this. The Newtonian result was this. So the only difference in terms of what you might call the force law, but probably shouldn't, is the presence of this term. There's good news and there's bad news. The good news is we have written out the differential equations that the u is going to have to obey. The bad news is this differential equation can't be solved in closed form. At this time, most people will then go off and start doing series expansions of one type or another to get approximate solutions to this. But me being me, I think I'm going to use a computer with an initial value solver to figure out what goes on in this equation. Until then, I hope everybody has a good day, and I'll talk to you again soon.